Hello, here we go with a bit of friction. We've got two forces acting in a vertical plane. So it's telling us two-dimensional, it's not three-dimensional. You know, these forces aren't skewed from each other. They're applied to a crate. Crate's got a mass of 50 kilograms. So let's just write that on there, 50 for the crate. Initially at rest on a rough horizontal surface. So we've got some friction. One force has magnitude of 80 newtons. So again, we're checking that all this is on the diagram. 8 newtons at an angle of 30, yep. 40 newtons at an angle of 20, yep. Force is shown in the diagram, that's fine. Right, they're giving us coefficient of friction of 0.6. Model the crate as a particle. Draw a diagram to show the forces acting on the crate. Right, so probably going to run out of space on this one because it's quite a wordy question, isn't it? There's our crate. We've got this 80 up here, which was at an angle of 30 degrees. We've got that 40, so this is copying the stuff they've given us, which is at an angle of 20 degrees. We've got the weight going straight down, which is 50g. We've got the reaction force going up, which I'm just going to call R. And then we've got the friction, which will be acting, well, let's say off to the left probably. We've got the larger force pulling things to the right. So I know it's at a slightly more oblique angle, but let's take the F going off this way. Yeah, make sure that you call it F. Don't put in the mu R bit because the force is the F. That's what we're saying is there. The mu R is a description of that force, so it's breaking it down a little bit further. So we've got the friction F. So draw all that on. Find the magnitude of the normal reaction force acting on the crate even. So we're doing, so this is Newton's second law, putting it on as usual, Newton's second, resolve vertically, and we're going to get that the resultant force, which is going to be 0. So going upwards, we've got an R, we've got a 40 sine 20 degrees, we've got an 80 sine 30 degrees, and that is going to be equal to 50g, because if you were strictly doing F equals ma, you'd say those three things going up minus the thing going down is going to be equal to 0 because the acceleration is 0. So I've just sort of dropped that step in order to say that they're equal in order for them to be 0 in total. So all we've got to do is type all of this in, and that is giving us that R is 436 newtons. Right, so that was a fairly painless start. Now we've got to, what have we just done? Right, we've done that bit, does the crate start to move when the two forces are applied to the crate? Right, so if we need to find the difference between these two horizontal forces. So let's do Newton's second again. So this time we'll resolve horizontally. And what we've got all in all is that 80 cos 30 degrees minus 40 cos 20 degrees, and then we can remove up to 0.6 times this 436. So we want to put all of this in, and then we've got minus F as well. And if that is greater than 0, then, so if that is greater than 0, then crate moves. Crate moves. Where, and we can say that F is up to a maximum of 0.6 times 436, which is 262 newtons. So let's put all of this in. We've got 80 cos 30 minus 40 cos 20. Let's just type in all of that in. 31.7. All right, so there's very little difference between these, which is pretty much what you'd expect. I suppose looking at it, it's only 80 and 40, so you're not going to get a very big difference between these two things when they got very similar angles. So, and we can take off, so minus 262 is putting us down at less than 0. So therefore, crate does not move. Obviously, F isn't going to be 262. It's actually just going to be the 31.7 in order to take it down to 0, so that there is no resultant force. But we've got a pot of F available, which is up to 262 newtons, and that is more than enough to wipe out this difference between the other forces. So that's fine. State 1, we are just about fitting in then. State 1 aspect of the possible motion of the crate that is ignored by modeling it as a particle. We've got a choice here of things. Yeah, if something's got dimensions, then we're looking at possibilities of it rotating or flexing and things like that. So let's go. You can go with either one of those. So you could say crate may rotate. That's probably. I mean, flexing is a similar sort of idea as well. But yeah, you might get some bending in it. The outer surfaces or whatever might be bending a bit. But rotation is a fairly safe one to go for as well. And they've only asked for 1, so you can't hedge your bets by putting 2 down and hoping that one of them's right. They asked for 1, then give them 1. So yeah, that's fine. So the main interesting part of this one is this third part here, where we're looking at this idea of limiting friction. Are we going to have a resultant force here when we've got a variable friction? So the friction can go up to 262 newtons. It doesn't have to. It's not a fixed value. It goes up to that, and then if we've still got some force left over, then the crate will start moving. Otherwise, the friction just acts up to the amount it needs to keep everything in equilibrium.